Section: Introduction. In this section, we address the challenge of aligning large language models, LLMs, in natural language processing, NLP. Our goal is to train models that are effective, safe, and controllable. To achieve this, we focus on fine-tuning LLMs to generate outputs with desired behaviors. Traditionally, the alignment of language models is based on a training objective involving the training data collection, a policy being optimized, a reference model, usually a supervised fine-tuned LM, and a reward model trained based on human preferences. Initially, reinforcement learning (RL) methods were used to align the model by first developing a reward model informed by human preferences and then tuning the LLM to produce outputs that maximize the reward model's values. The current approach involves more complex reparametrization, such as directly optimizing the LLM by maximizing the likelihood of the training data. We introduce a new training process called Trust Region Direct Preference Optimization, TR-DPO, which updates the reference policy during training either by integrating it with the optimized policy or by replacing it after a certain number of steps. Our contributions include showing that TR-DPO outperforms traditional DPO, especially with a 0.6 alpha value, leading to a 19% higher win rate in model pair comparisons using GPT-4. We test the efficacy of TR-DPO across different natural language generation tasks and model sizes, demonstrating its superiority in human-centric metrics like coherence, correctness, level of detail, helpfulness, and harmlessness. We also analyze the impact of different alpha and tau settings on generation diversity, finding a strong correlation between KL divergence and generation length. The alignment process is crucial for developing chat assistants that provide safer, more helpful, and truthful responses, ultimately enhancing user satisfaction. Reinforcement learning from human feedback, RLHF, has been instrumental in the success of advanced LLMs like GPT-3.5, GPT-4, and Llama 2, involving stages like SFT model training, training, and the PPO algorithm. While RLHF has its challenges, direct preference optimization, DPO, and other methods have addressed some issues by redefining optimization problems and training models directly without RL algorithms. Our proposed strategy involves updating the reference policy during training, similar to updating the target network in reinforcement learning algorithms. We focus on enhancing the widely used DPO algorithm by eliminating limitations related to the closeness of the trained policy to the reference policy. Our method aims to improve alignment by updating the reference policy throughout training. Section Summary. In this section, we address the challenge of aligning large language models, LLMs, in natural language processing, NLP, by introducing Trust Region Direct Preference Optimization, TR-DPO. TR-DPO updates the reference policy during training, either by integrating it with the optimized policy or replacing it after a set number of steps. Our method outperforms traditional direct preference optimization, DPO, showing a 19% higher win rate in model pair comparisons using GPT-4, and significantly improves human-centric metrics like coherence and correctness, validated on the Anthropic HH dataset. Section: Method. In this section, we aim to explain the method we used for aligning objectives and updating the reference policy during training. The alignment objective involves regularizing with a fixed reference model to maximize reward while staying close to the reference model. We wanted to transition from a static reference model to an updated one during training. To achieve this, we updated the reference policy parameters interactively using two main methods. The first method is called soft update, where a weighting factor alpha between 0 and 1 determines how quickly updates affect the reference policy. Since both the policy pi_theta and the reference policy pi_ref start with the same parameters, a soft update is justified. The second method is the hard update, which occurs every tau training steps. This method involves directly replacing the reference model with the updated policy after a certain number of training iterations denoted by tau. Updating the reference policy raises a question: How does it impact the training objective? One way to understand this is by connecting it to Trust Region Deterministic Policy Optimization, TR-DPO, methods. By controlling the frequency of changes in the reference policy, TR-DPO strikes a balance between the vanilla objective and trust region variance. The parameters of TR-DPO, such as alpha and tau, are chosen based on this connection. Moving on to the experiments, we evaluated different training configurations on two datasets, Anthropic HH and Reddit TLDR summarization. The Anthropic HH dataset consists of pair preferences for SFT and preference learning, while the Reddit TLDR dataset includes human preference judgments on model-generated summaries. We used various Pythia models with different sizes and explored two main update strategies: soft update, TR-DPO-alpha, and hard update, TR-DPO-tau, to assess their impact under different conditions. To evaluate the performance of TR-DPO configurations against the DPO baseline, we employed Auto-SXS evaluation and human-centric metrics evaluation frameworks. The Auto-SXS framework used GPT-40125 preview to analyze preferences across 500 samples, while human-centric metrics like coherence, correctness, detail, helpfulness, and harmlessness were scored on a scale from 1 to 10. Additionally, we conducted diversity analysis to understand how our methods balance alignment and generative diversity during training. Section Summary. In this section, we introduce two primary methods for updating the reference policy during training: soft update and hard update. The soft update involves gradually merging the current policy with the reference policy using a weighting factor alpha, while the hard update directly substitutes the reference model with the updated policy after a specified number of training iterations tau. These methods, denoted as TR-DPO-alpha and TR-DPO-tau respectively, allow for controlled adjustments to the reference policy, impacting the training objective and influencing the learning trajectory of the model. Section: Performance comparison on two tasks. In this section, we compared the performance of two tasks and found that both TR-DPO's soft and hard update strategies improved performance compared to the traditional DPO approach on the Anthropic HH and Reddit TLDR datasets. We analyzed the effectiveness of different alpha values in the soft update strategy and various tau intervals in the hard update strategy for both datasets using the Pythia 2.8b model size. Our evaluations, confirmed by both GPT and reward model assessments, showed that TR-DPO with alpha between 0.5 and 0.7 consistently outperformed higher alpha values and the baseline DPO. Additionally, we observed that TR-DPO-tau performance improved as tau increased from 32 to 512 but slightly decreased at tau equals 1024. These results emphasize the importance of selecting suitable update parameters to avoid hindering the model's performance. To conduct a detailed analysis, we used the POI metric to assess coherence, correctness, level of detail, helpfulness, and harmlessness on the Anthropic HH dataset. The analysis showed that optimal settings for alpha and tau are crucial for maximizing TR-DPO's performance, with fine-tuned settings leading to better dialogue quality based on HC metrics. We also found that TR-DPO-alpha performed best around alpha equals 0.5 to 0.6, while TR-DPO-tau showed optimal performance at tau equals 256 and 512 across different datasets. Furthermore, we extended our analysis to include a range of Pythia model sizes, demonstrating TR-DPO's ability to enhance model performance across various complexities. It was observed that precise selection of alpha and tau is essential to achieve a balance between adherence to the SFT policy and adaptability for effective training and output. We also explored how updating the reference policy affects generation diversity, showing that variations in alpha and tau values influence generation diversity. Careful tuning of these parameters is crucial to optimize TR-DPO performance while maintaining output quality. Section Summary. In this section, we compare the performance of TR-DPO's soft and hard update strategies with traditional DPO on the Anthropic HH and Reddit TLDR datasets, showing that TR-DPO outperforms the baseline DPO approach. By adjusting parameters like alpha and tau, we demonstrate that selecting appropriate update parameters is crucial for maximizing TR-DPO's performance, as too frequent updates or excessive trust in new policies can hinder model performance. Additionally, our analysis using the POI metric highlights the importance of fine-tuning alpha and tau values to enhance dialogue quality and model output, emphasizing the direct link between parameter calibration and improved model performance. Section on the gradient dynamics. In this section, we examine the impact of different reference policy update methods on the training process. We focus on the gradient of the loss function as shown in equation. The term involving the logarithm ratios of probabilities acts as a weighting factor, indicating the difference between the outcomes of the trained policy and the reference model. When the trained policy assigns a higher probability to the preferred outcome compared to the reference model, the gradient magnitude becomes small. Conversely, when the trained policy assigns a lower probability to the less preferred outcome, the gradient magnitude also decreases. During training, we keep track of the gradient scale for the DPO and both update strategies. These gradient scales are smoothed for clarity and shown in a figure. We propose that there is a connection between the observed gradient scales and the training dynamics. Specifically, higher values of alpha in soft updates and lower values of tau in hard updates lead to increased gradient scales, which could indicate higher training instability. This instability could cause a significant deviation from the stability of the SFT policy, resulting in performance degradation. On the other hand, a balanced selection of alpha and tau seems to promote better convergence by controlling the frequency and scale of policy updates. This balanced approach ensures a stable path towards refining the optimal policy.